Hello everybody, welcome into another lesson. So today we are going to do part 2 of exponential functions, in which today we're going to talk about exponential decay. Now in the last lesson we talked about exponential growth, which has big applications in the financial and accounting aspects. In financial growth, that's how you can find compound interest and find the amount in an account with compound interest after so much time. Exponential decay, on the other hand, is very useful, especially in the sciences, the nuclear sciences. For example, when, let's say, there's a release of uranium or a nuclear bomb or something, right? And over time, of course, the radiation breaks down in its half-life, and it'll decay exponentially, but it never fully goes away. It never fully goes back to zero. Now it can reach a point where it's like zero, but it never 100% goes away. That's this idea of exponential decay. So let's get into this here. Here you have y equals 2 to the negative x. So this time we have 2 to the negative x power. Well, let's graph this. So let's start where x is 0, right? That would be 2 to the negative 0, which is just 2 to the 0. That would still be 1. Alright, now let's put negative 1 in for x. 2 to the negative first is actually 2 to the positive first, which would give you 2. So at negative 1, you'll get a y value of 2. And then let's put in negative 2. Which would give you 2 to the second, which would give you 4. So when x is negative 2, you would get a y value of 4. And then why don't we do negative 3 for x? So 2 to the negative 3 is 2 to the third, which would be 8. So at negative 3, you would be all the way up to a y value of 8. Now let's go in the positive direction with x. When you have 1 in there for x, that's 2 to the negative first, which is 1/2. So you would have the point 1 1/2. Now how about when x is 2? So you would have 2 to the negative second, which would end up being 1/4. So you'd be about down there. And then you see you get infinitely closer and closer to 0. Like if I did 3, you would have 2 to the negative third, which is 1/8. If I did 4, you'd have 2 to the negative fourth, which is 1/16, and it just gets infinitely closer and closer to 0. So let's go ahead and graph this bad boy here. Alright, so you see what we got here. This is called exponential decay. Over time, it decays exponentially, but it never actually reaches 0. You have a horizontal asymptote yet again at y equals 0, because the idea of an exponential function is, again, there will be no value that you can raise this to that would actually make the y value 0, or negative for that matter. So that's why the asymptote is y equals 0. And it helps guide the curve. Now, what is another way of saying 2 to the negative x? 2 to the negative x is what? Isn't that the same as saying 1 over 2 to the x? Isn't 2 to the negative x 1 over 2 to the x? Well, here's the thing also. 1 to any power is 1, right? Any power. So this can actually be rewritten as 1/2 to the x power. So this y equals 2 to the negative x is going to be the exact same as that 1/2 to the x power, to the positive x. So here's how you know you have exponential decay. Let's write the general form, where y equals a times b to the x minus h plus k. That's the general form of an exponential function, right? As we covered in the last lesson, where a is still greater than 0. So your a is positive. But this time, your b, right? If b is a whole number to a negative exponent, or b, here, let me write this better, or 0 is less than b, which is less than 1, to a positive exponent, you have exponential decay. So, your a, which is simply the coefficient you're multiplying the exponential function by, would be greater than 0, just like it would for exponential growth. But this time, if that base is a whole number to a negative exponent, like we have here, 2 to the negative x, that's the same thing. If you take a whole number to a negative exponent, isn't that the same as the reciprocal to the positive exponent? Well, that's this idea. Or 0 is less than that base, which is less than 1. So that base, in other words, is either a fraction or a decimal greater than 0 but less than 1. You have exponential decay. And then that x minus h, of course, indicates a shift either left or right horizontally for the function. That plus k indicates either vertical shift up or down, which we'll get into some examples like that here. So, in fact, let's do this. All right, what do we got here? Now we have y equals 4 times 3/8 to the x power. So you have a coefficient on the exponential function of 4, but you have the base is less than 1 raised to a positive exponent of positive x. So again, start at x is 0, right? X is 0. What is 3/8 to the 0 power? That's just going to be 1 times 4 puts you all the way to 4. So you would have the 0.04. All right. Now, what about when x is positive 1? Well, that would be, of course, 3/8 to the first power is 3/8. What's 4 times 3/8? That's 3/2, which is 1.5. So at 1, you're going to go all the way down to 1.5. Now, what about you raise 3/8 to the second power? What would that give you? So 4 times 3/8 raised to the second power. Well, 3/8 to the second power, that's going to be 9/64, right? What is 4 times 9/64? That's going to equal 9/16. So when x is 2, that'll be just a little over half for your y value. Now what about, for one more here, let's do 4 times 3/8 to the third power. Well, what is 3/8 to the third power? So this will be 4 times 27 over, oh gosh, What is 8 to the third power? That's 64 times 8. I don't have my calculator on me because my phone's charging. So what is 64 times 8? That's 512. Okay, so that's going to be 57 over 512, which would be the same as 27 128ths. So when x is 3, that's pretty low, 27 128ths, and you see it keeps getting infinitely smaller, closer to 0. Now let's do this in reverse, right? Let's take a few values at the negative values of x. So we would take x at -1. So 4 times 3/8 to the negative first. Well, 3/8 to the negative first, if it's a negative power, it's the reciprocal to the positive first power, right? So that'd be 4 times 8/3, which would give you 32/3. That's just a little bit south of 11. So that's going to be all the way up here somewhere when x is -1. Now, if you take it to the -2, it's going to go even higher. The point is, it's growing exponentially. So you have a huge stretching factor there of 4. And it follows this line here. So this is an example, again, of exponential decay because your base is less than 1 raised to a positive power. And then that 4 is just a coefficient, a stretching factor, if you will. All right. Now, what if I take 8 times 7 to the -x power? So I'm going to take 8 times 7 to the -x power. So I have my coefficient of 8 that I'm multiplying this by. But notice I have a whole number raised to a negative power. So if it's a whole number raised to a negative power, this is also exponential decay. So let's take x when it's 0. So what is 7 to the 0 power? That's 1 times 8 is 8. So you'll be all the way up at 1/8. That's pretty far up there. Huge stretch factor. Now, what about when x is 1, right? So you would have 8 times 1/7, right? So that would be 8/7. That would be a little bit over 1. Now what about to the second, when you put 2 in for x, that would give you 8/49, right? So that's pretty dang low. And it just keeps getting infinitely smaller. Now let's put in -1 for x. That'd be 8 times 7, which would be all the way up at 56. That's going to be somewhere way out there. Let's just put that up here arbitrarily. I know it's going to look way different than that, but hold on a minute. I done and butchered this. It's going to look something like that, a huge stretching factor, but the more to the point, this is exponential decay. But look how vertical it is. Look how tall it is. It almost stands straight up at some points. So another example of exponential decay. Now, let's see here. What if we had something like y equals 1/2 to the x minus 1. So y equals 1/2 to the x minus 1. Well, Your coefficient's 1, so that makes life easy, but your base is 1/2 raised to the x minus 1 power. What matters here is that the x is to the x coefficient's positive, so that means your base is to a positive x power, and the base is less than 1 but greater than 0, so this is also exponential decay. But what that x minus 1 means is everything is shifted over to the right. So you're actually going to, if you take x minus 1, set it equal to 0, you would get the point that x starts at 1. So let's pick when x is 1. Of course, 1 minus 1 is 0. 1/2 to the 0 power is 1. So you would get the point 1, 1. Now, what about 2? When x is 2, well, 2 minus 1 is 1. 1/2 to the first power is 1, so you would get the point 2, 1/2. Alright, so when x is 3, 3 minus 1 is 2. 1/2 to the second power is 1/4. So you get the point 3, 1/4, and you see it keeps getting infinitely smaller and closer to 0 without actually reaching it. Okay? Now, what about when x is 0? Well, 0 minus 1 is negative 1. 1/2 to the negative first power, that's the same as 2 to the first power. So you would get the point 0, 2. Now, what about when x is negative 1? So negative 1 minus 1 is negative 2. 1/2 to the negative second is the same as 2 to the positive second, which would be 4. So you would get the point negative 1, 4. Now, what about, let's make x negative 2. All right, so negative 2 minus 1 is what? Negative 3. 1/2 to the negative third is the same as 2 to the positive third. That would give you 8. So you would get the point negative 2, 8. And now we are ready to proceed with drawing the curve. And there's your curve of 1/2 raised to the x minus 1 power. Shifted everything to the right 1 unit. Also something to notice too, when you have exponential decay, how it reflects the original, it'll reflect, like let's say I was taking 2 to the x minus 1, that would be going like this. It would go like that. Well, you have a reflection in the y-axis whenever you have exponential decay. So that's something else to keep in mind. It reflects in the y-axis whenever you have decay from the original exponential growth function. Okay. Shouldn't have too many more. Now, what if I do this? I slap on a coefficient here. So I have negative of 1/4 raised to the x power. So how's this going to affect the graph when I have a negative coefficient? Well, let's start x equals 0. So what is 1/4 of the 0 power? That's 1. But that'll actually, you negate that, you'll actually be at negative 1. So you'll get 0, negative 1 for a coordinate. Alright, what about when x is negative 1? That'd be 1/4 to the negative first power, which would be 4 to the first, so you would end up getting 4. You negate that, you get negative 4. 2, 3, 4, so you would end up getting negative 1, negative 4. Now what about when you have x to the negative second? So 1/4 to the negative second is the same as 4 to the second, which is 16. Negate that, you'll end up getting negative 16, which will just put you way down here somewhere. And then you're going to, let's go the opposite direction. So when x is positive 1, well, 1/4 to the first power is 1/4. You negate that, you get negative 1/4. So when x is 1, you'll be at negative 1/4 for your y value. And then for good measure, let's do let's do the second. 1/4 to the second power is 1/16. You negate that, you'll be at negative 1/16 for your y. Now we can draw this curve. And it doesn't look exactly like that because at -2 it'd be down to -16, but it's going to look roughly like that. My board only goes up to 10 units, but as you see, if you slap a negative coefficient on this, it reflects the decay function in the y-axis. So that's what you would have. And your asymptote is still at y equals 0. It increases up until y equals 0, gets infinitely close to 0, but never actually reaches it whenever you have a negative coefficient on an exponential decay function. Now, what if I took 1/2 to the x plus 1, all that minus 1? So what are we doing here? We have 1/2, that quantity raised to the x plus 1 power, all that minus 1. So okay, so we know this is exponential decay, right? Because you have your base is greater than 0 but less than 1, and it's raised to a positive x power. Now also, you have the x plus 1 power, which means it shifts everything 1 unit left. You're going to go 1 unit left, and then all that minus 1 tells you you're shifting everything downward 1 unit. That's a vertical shift downward of 1 unit with that minus 1. So let's graph this. Set x plus 1 equal to 0, you would get a x equals -1. So you'll actually start where x is -1, okay? So -1 plus 1 is 0. 1/2 to the 0 is 1. 1 minus 1 is 0. So you would be at the point -1, 0. Now, what about when x is -2? So -2 plus 1 is -1. Well, what's 1/2 to the negative first? That's the same as 2 to the first, which is 2, minus 1 is 1. So at -2, you would be at a y value of 1. Now, what about when x is -3? -3 plus 1 is -2. 1/2 to the negative second is the same as 2 to the second, which is 4, minus 1 is 3. So at -3, you'd be all the way up to 3. Let's do x equals, let's do -4 for x. So -4 plus 1 is -3. 1/2 to the negative third is the same as 2 to the positive third, which is 8, minus 1 is 7. So at -4, you'll go all the way up to y equals 7. Okay, let's go the opposite way now. What about when x equals 0? X equals 0, so that's the same as 1/2 to the first, which is 1/2. Well, what's 1/2 minus 1? That's -1/2. So you would end up being at 0, -1/2. All right. Now, what about when x is 1? 1 plus 1 is 2. 1/2 to the second is 1/4. Minus 1 is -3/4. So you'd be all the way down to -3/4 for your y. And then, heck, for good measure, let's do x is 2. So 2 plus 1 is 3. 1/2 to the third is 1/8. Minus 1 is -7/8. So notice, let's graph this real quick here. Let's go left first. And then it comes down. And it goes all the way down to almost where y equals -1. It gets infinitely closer to a y value of -1, but it never quite reaches it. So, just like with exponential growth, your vertical shift, whether up or down, is going to tell you that your horizontal asymptote, in this case, is y equals -1. That vertical shift is always your horizontal asymptote. So y equals -1 is your horizontal asymptote. You have literally shifted everything downward 1 unit. So here is your horizontal asymptote at y equals -1. And let's do one more here. One more for good measure, then we're done. This time I'm pulling out all the stops. Let's say, good one, we have the negative of 1/3 to the x minus 1 power plus 3. So we have the negative of the quantity of 1/3 to the x minus 1 power, all that plus 3. So look at our base. That's 1/3, which tells you, and it's raised to a positive form of an x power, which means you have exponential decay. And that x minus 1 means you're going to shift everything to the right 1 unit. That negative sign means you're going to dump it and reflect it in the x-axis. And then that plus 3 tells you you're going to shift everything upwards 3 units. And remember, that plus or minus the number outside of the exponent, so the vertical shift upward 3 units tells you that your horizontal asymptote is going to sit at y equals 3. So that means your graph, your values for y will get infinitely close to 3 but never quite reach it. It'll get infinitely close but never actually get it. So, okay, x minus 1, let's set that equal to 0. That tells you x starts at positive 1. So let's go there now. 1 minus 1 is 0, right? 1/3 to the 0 power is 1. You know, why don't we draw our asymptote first? That might help us, right? Yeah, let's draw this asymptote at y equals 3, just to illustrate that we're not actually going to hit it. Okay. So yeah, anyway, 1/3 to the 0 power is 1. Negative of that is -1 plus 3 is 2. So at 1, you'll get a y value of 2. Okay, so now what about when x is 2? Well, 2 minus 1 is 1. What's 1/3 to the first power? That's 1/3. You negate that, you'll end up getting -1/3 plus 3. That's going to be positive 2 2/3. So when x is 2, you'll get 2 2/3. Alright, for one more, let's do when x is 3. What's 3 minus 1? That's 2. Well, what's 1/3 to the second power? That's 1/9. Negate that, you get -1/9 plus 3. That'd be positive 2 8/9. So you see you're getting infinitely closer to 3, but you're not actually able to pull your act together and quite reach it. Now, let's do when x is 0. So when x is 0, you get -1. What's 1/3 to the negative first power? That's the same as 3 to the positive first, which would just be 3. If you negate that, you get -3 plus 3 is 0. So when x is 0, y is also 0. So you'll have the point 0, 0. Now, what about when x is -1? -1 minus 1 is what? That's -2. What is 1/3 to the negative second? Well, that's the same as 3 to the second, which is 9. You negate that, you get -9 plus 3 is -6. So at -1, you'll get a value of -6 for your y. And as you see, it just keeps getting infinitely, it keeps going down infinitely. So let's draw that curve here. And there's your curve. You've reflected it, of course, in the x-axis. You've shifted everything to the right 1 unit, and you've shifted everything up vertically 3 units. And it gets infinitely closer. The more you increase your x values, it gets infinitely closer to 3 without actually reaching a y value of 3. So that's it for the exponential decay lesson for part 2 of exponential functions. Next lesson, we're going to talk about the number e. We're going to finally introduce the number e and why that is so important. It's going to be very important, especially if you go on into engineering and calculus and even financial fields in accounting. It also goes for continuously compounded interest. There's so many applications of e. So I hope everyone has a great day. Take care.